Hello everyone and welcome back to Math 143, Finite Mathematics. In our previous lecture, we studied compound interest, continuous compounding, effective interest rate and present value. In all of those problems, we usually considered one initial deposit which we called the principal amount. Today, we are going to study situations like involving a sequence of regular payments. For an example, depositing money into retirement account every month, making monthly loan payments, paying rentals, or receiving regular payments from an investment. So those are the sequence of equal payments made at regular time intervals, which is called an annuity. So by the end of today's lecture, you should be able to define an annuity, distinguish between an ordinary annuity and annuity due, calculate the future values of an ordinary annuity, calculate the present value of ordinary annuity, and identify annuity formula should be used in a given problem. Okay, let's begin with the definition. First of all, what is an annuity? An annuity is a sequence of equal payments made at regular time intervals. An annuity is a sequence of equal payments made at regular time intervals. Okay, the payment must be equal and they must occur regularly. The important thing, the payment must be equal and they must occur regularly. Right. Let's see the example. For an example, suppose you deposit $200 at the end of every month. At the end of every month into a retirement account. So that is an annuity because every payment is $200. Also, every payment are made monthly. Monthly. So this is an annuity. So what are the other common examples? Monthly loan payment, quarterly retirement contribution, yearly insurance payments, monthly rent payments, okay. Then we wanted to know the types of annuities. So there are two main types of annuities. The first one is an ordinary annuities. The ordinary annuity, those payments are made at the end of each period. Payments are made at the end of the time period or of the each period. What are the examples? Examples: a deposit made at the end of every month. A loan payment made at the end of every month. So the ordinary annuity made at the end of every time period, each time period. And the second one is the annuity due. The second type, annuity due. So the annuity due, those payments are made at the beginning of each period. So a common example is rent. You usually pay rent at the beginning of the month. So for this section, we will mainly focus on ordinary annuities, but we will discuss the annuity due also. Okay, let's go for the example then. Think about if I deposit $500 at the end of every month. If I deposit $500 at the end of every month, is that an ordinary annuity or an annuity due? So this should be the ordinary annuity at the end of every month, right? Okay, then if I pay rent on the first day of every month, if I pay rent on the first day of every month, so this is annuity due. right? I hope now you can recognize the difference between, you can identify the distinguish between ordinary annuity and the annuity due. Okay, then let's go for the next important concept. That is the future value of an ordinary annuity. Future value of an ordinary annuity. So, the future value of an ordinary annuity is the total amount accumulated after all payments have been made and interest has been earned. So, that is the total amount of accumulated after all payments have been made and interest has been earned. Okay, suppose it money regularly into a retirement account. Suppose you deposit money regularly into a retirement account. So then each payment earns interest for different amount of time. Each payment earns interest for a different amount of time. That means the first payment earns interest for the longest time. The first payment earns interest for the longest time. Right? So, the final payment earns little or no interest before the account is evaluated. Also, the final payment earns little or no interest before the account is evaluated. So then rather than calculating the value of every payment separately, we use the future value formula. So rather than calculating the value of every payment separately, we use the future value formula. Right? So then let's see the future value formula. The future value formula, you can see the notes. The future value FV equals R times, here R is the payment made each time period, then 1 plus I to the power n. Here I is the interest rate per period, not the annual interest rate. It should be the interest rate per period. And n is the total number of payments minus 1 over I, where R the total, the payment, not the total, the payment made each period, and I the interest rate per period, n the total number of payments. I hope you remember the formulas for I, which is R over M. Here R is the annual interest rate. And M is number of conversional period. And N, M times T, where T is time in years, M is number of conversional period. Okay. So let's see. The most important details in annuity problems. Matching the interest rate and payment period. Matching the interest rate and payment period. So the interest rate period must match the payment period. If the payments are monthly, use the monthly interest rates. So that is why I recall this I equals R over M. So if payments are monthly, use the monthly interest rate. If payments are quarterly, use the quarterly interest rates. Okay, let's see the example, how to get the monthly, quarterly, or the interest rate per period. So, for an example, if annual interest rate is 6% compounded quarterly, so then I equals R over M, 0.06 over 4, 0.015. So we should use the quarterly interest rate to calculate the future value. Okay, then let's see how to get the payment period. So that is why recall n equals m times t. Again, let's say if payments are made for 10 years, quarterly 10 years, then n equals 4 times 10, 40 time periods. Always calculate I and n before substituting into the formula. Right, very important. Always calculate I and n before substitute. Right. Okay, now let's go for the future value example. Let's compare the two retirement investors, Sammy and Josh. Okay, example 1. Compare two retirement investors, Sammy and Josh. Okay, Sammy deposit $600 at the end of every quarter from age 25 until 65. Okay. Then Josh deposits $1,000 at the end of every quarter from age 35 until age 65. Okay, who will have more money at age 65? Both accounts earn 6% per year compounded quarterly. Okay, let's see the information, more info. Both accounts earn 6% per year compounded quarterly. Okay, the question is who will earn or who will have more money at age 65. Okay, now let's begin with Sammy. With the information, the Sammy's account start with the payment of at the every quarter $600 starting from 25 years until 65. Okay, so let's go for the Sammy's account. Okay. Her payment is $6,000. That means our regular payment value. And quarterly interest rate quarterly interest rate I equals 0.06 over 4, 0.015. She contributes how many years? 65 minus 25, 40. So she contributes for 40 years quarterly. Therefore, n equals 4 times 40, 106. Then let's substitute. Now we have all the information. Then substitute into the future value formula. So future value equals R times R times 1 plus I to the power n minus 1 over I. We have R 600, 1 plus I 0.015 to the power 160 minus 1 over 0.015. Then let's simplify. The future value 600, 1.015 to the power 160 minus 1 over 0.015. You can use your calculator. So 600, 10.828 minus 1 over 0.015. The future value $393,138 and 46 cents. So using calculator, you can get that value. So Sammy will have approximately the future value 393,138. Okay, now let's calculate Josh balance. So his payment is regularly $1,000, same interest rate. The periodic rate is still 0.015 because 6% over quarterly, right? Then just starting from 35, right? Just starting from 35 until age 65. Therefore, Josh contributes for 30 years. 65 minus 35, 30. So Josh contributes for 30 years. Then n equals 4 times 30. 30 years quarterly, 120. Therefore, the future value substitute the values 1000, 1 plus 0.015 to the power of 120 is approximately, using your calculator you can get the value. Approximately the value should be 331,288 and 19 cents. So Josh will have approximately okay. Then even though Josh deposits more money each quarterly, because the amount that Josh has deposit every month is $1,000. So even though Josh deposits more money each quarter, Sammy ends with more money. Why? Because Sammy began investing 10 years early. Therefore, her early deposits had made more time to earn compound interest. So let's say the interpretation. Even though Josh deposits more money each quarterly, that means 1000 greater than 600. So Sammy ends with more money. Then why? So the answer should be because Sammy began investing 10 years early. So her early deposits had more time to earn compound interest. Right? So this example illustrates very important financial lesson. What? Time can be more powerful than a larger payment. Okay, then let's go for the example. One more example. Let's call one more example. Example 2, monthly deposits. A person, let's say, a person deposits $200 at the end of every month. For 8 years into an account earning 5% compounded monthly. Find the future value. find the future value. So we wanted to find the future value at the end of 8 years. A person deposits $200 at the end of every month. That account earns 5% interest rate compounded monthly. Okay, let's do this one step by step. Let's identify the payment amounts and the most important details, right? Step 1, the payment R. Identify the payment. R equals $200 every month. Then step 2, with the given interest rate and the compounded monthly, the periodic rate. Find the periodic interest rate. Since interest is compounded monthly, I equals R over M, 0.05 over 12. So 0.05 over 12, what would be the value? 0.00416. You can use both decimal, either decimal or the ratio. Next, find the number of payments. Step 3, there are 12 monthly payments each year for 8 years. There are 12 monthly payments each year for 8 years. Then N equals 12 times 8, 96. 96 number of payments. Then step 4, substitute into the formula. FV equals R times 1 plus I to the power n minus 1 over I. So the future value R, $200, 1 plus I would like to use this 0.00416 to the power 96 minus 1. What about the final value? Using calculator, the future value could be approximately $23,548.10. Therefore, account will contain approximately, account will contain approximately $23,548.10. Okay, then let's compare the contribution and the interest for the same example. So compare the contribution and interest. Think about how much money did the person personally deposit? How much money did the person personally deposit? So every month, at the end of every month, $200, the payment time period 96 months. So $19,200. At the end, the person account has the amount 23,548. The person contributes $19,200. Therefore, interest earned 23,548 and 10 cents minus 19,200. The earned interest value 4,348 and 10 cents. So approximately 4,348 cents came from interest. Right? Okay. So far, we have made regular deposits and asked how much money will accumulate in the future. Now we wanted to reverse this question. Suppose a company promises to make regular payments to you in the future. Then, what are those future payments worth today? That question involves the present value of annuity. Okay, let's go for the present value. So, suppose a company promises to make regular payments to you in the future. So, what are those future payments worth today? So that question involves the present value of the annuity. Okay, then let's see the definition. The present value of an ordinary annuity. Okay, the present value of an ordinary annuity is the value that today of a sequence of future payments. So that is the value today of a sequence of future payments. So, that the formula calls present value with the amount, the regular payment amount, 1 minus 1 plus I to the power negative n over I. Here R is the regular payment, I again R over M, the interest rate per period, N, the number of payments, again M times T, number of payments. Okay, then let's see how to choose between future value and present value. So, first of all, ask yourself one question. Where in time is the value being requested? Where in time is the value being requested? Use future value when the question asks how much will be accumulated? How much will the account contain later? What will the retirement balance be? Use the present value when the question asks, what is the cash price today? How much is a stream of payment worth now? How much money is needed today to fund future payments? So, it is very important to choose between future value and present value. Therefore, how to choose between future value and present value. So, use future value when the question asks how much will be accumulated. How much will be account contain later. What will the retirement balance be? So all those questions ask the how much at the end of the time period, the future value. Then use present value when the question asks what is the cash price today? What is the cash price today? How much is a stream of payments worth now? Also, how much money is needed today to fund future payments? Right? Okay. Then let's see the example. It says Mike's Sporting Goods sells an elliptical trainer using an installment plan. So Mike's Sporting Goods sells an elliptical trainer using an installment plan. So the customer pays $22 at the end of every month for 3 years. 3 years. Interest rate is 9% per year, compounded monthly. Find the equivalent cash price today. Find the equivalent cash cash price today. Okay. It says the customer pays $22 at the end of every month for 3 years to get the installment plan, get the elliptical trainer with the installment plan, and the interest rate is 9% per year compounded monthly. If another customer says if he gets the cash price to get it, then what should be the cash price today? So first of all, identify, is this a future value or present value? This is a present value because find the equivalent cash price today. Now on, what about the value? So then let's go for the step-by-step solution. Step 1, identify the payment. So the monthly payment, $22, that would be the R. Step 2, find the monthly rate. Since the question given 9% per year compounded monthly, therefore I equals 0.09 over 12, 0.0075 monthly interest rate. Then step 3, find the number of payments. Three years, monthly payments. So M times T, 12 times 3, 36 equal payments. Then use the present value formula to find the cash price today. Use the formula, present value formula. So let's use the present value formula. PV equals R times 1 minus 1 plus I to the power negative n over I. Substitute the values. Approximately the value 691 and 83. Using your calculator, you can get that value. Therefore, the equivalent cash price is approximately $691.83. Okay, so notice that the total of the installment payment is 22 times 36. So let's see the interpretation. The total of the installment plan or installment payments $792. However, the cash price is only about $691.83. Cash price. So why are they different? Because money paid in the future is worth less than money paid today. Because money paid in the future is worth less than the money paid today. So the additional amount paid through the installment reflects the cost of financing. It through the installment reflects the cost of financing. Okay, let's go for the one more example quickly. Example, find the present value of receiving for $1,000 at the end of every year for 10 years if the interest rate is 6% annually. 6% annually. Okay, let's quickly find out the informations. Identify the values. R $1,000, I R over M annually, therefore 0.06 over 1, 0.06. N equals M times T, 1 times 10, 10. Then substitute it into the equation. PV equals R times 1 minus 1 plus I to the power negative N over I. Okay, use your calculator to get the present value 7,360 and 09 cents. Therefore, the present value of those 10 future payments would be 7,360 and 09 cents. The future value, the present value of those 10 future payments, 7,360 and 09. Let's see the total future payments adding to. The total future payments add to 1,000 times 10, 10,000. So, but their value today is only about 7,360 and 09 cents. But their value today is only about 7,360 and 09 cents. That is because most of those payments will not be received until several years from now. Right? Okay, here I will give you the more practice examples. Please make sure to pause the video and practice the future value and present value exercises. You deposit $150 at the end of every month for 5 years into an account earning 4.8% compounded monthly. So first identify the values R, I, and N. Then use the future value formula. Okay. Next one. A loan requires payments of $350 at the end of every month for 4 years at 7.2% compounded monthly. Okay, find the original loan amount today. Right? So, is this a future value or present value? This should be the present value because we want to amount borrowed today. Next one. So decide which formula applies. First one. How much will monthly retirement deposits grows to? Decide whether this is a future value or present value. Second, what is the current value of future loan payment? Third, how much will a savings account contain after regular deposits? Account contain after regular deposits. Lastly, what is the cash price equivalent to an installment plan? So, let's review several common mistakes. So, there are several common mistakes that the student can make using the annual interest rate instead of the periodic rates, forgetting to calculate the total number of payments periods, and using the future value formula when the question asks for value today, using the present value formula when the question asks for the accumulated balance at the future, assuming that n, lowercase letter n, is the number of years rather than the number of payment periods, entering the negative exponent incorrectly into the calculator. So I would happy to give you the calculator guidance. Enter the expression in separate parts when necessary. So enter the expression is enter the expression in separate parts when necessary. Okay, the first one, for future value, calculate, step 1, calculate 1 plus I. Second, raise 8 to the power n. Subtract 1 from 1 plus I to the power n. Fourth, divide by I. Fifth, the last step, multiply by R. Also, for present value, first calculate 1 plus I, and second calculate 1 plus I to the negative power. Third, subtract that results from 1. Fourth, divide by I. Fifth, multiply by R. Okay, those are the steps. So then let's summarize today's lesson. An annuity is a sequence of equal payments made at regular intervals. An ordinary annuity has payment at the end of each period. Also, we use the future value formula when we want to know how much regular deposits will accumulate to in the future. We use the present value formula when we want to determine what a sequence of future payments is worth today. For every problem, remember to identify the payment R, the periodic interest rate I, and the total number of payments N. The most important first step is deciding whether the problem asks for future value or a present value. Okay, I hope everything works well. Then thanks for watching. I'll see you in the next lecture.